Okay. So you definitely heard of hertz. We said that 1/2 is in hertz, and actually hertz is actually it comes from the name of a German scientist. His name is Heinrich Hertz, who actually was the first one to demonstrate experimentally the link between Maxwell equations and electromagnetic waves. And his experiment is actually quite simple. Because remember, this is in 1857 to 1894. So he only lived very, very short, but his experiment in 1887 was tremendous. And this is why now we use hertz as a unit, okay? So what did he do? Well, what he did is the following, is that he took a high voltage source, a battery, okay? And he connected to a wire here, with two conducting spheres. These two conducting spheres, they do not touch each other, but they are very close to each other. Okay, and so when the voltage is high, they will make a spark between them. Okay, and so he was able to generate sparks between these two conducting spheres. Okay. On the other hand, far away, he simply had a wire. What you can see is a wire, and with two sparks as well. Okay. And so, what he wants to test is that, okay, I have now two things which are completely different. They have nothing to do with each other. I could put this part here, which is what we're going to call the emitter, at one side of the room, and the other part, where it does not contain anything, on the other side of the room, and see if there is an actual link between the two. Okay? And how to detect the link in 1887? Simply by seeing the spark. Okay? So on one hand, he can see the spark happening when he applies the high voltage source on the emitter, and then he could go and he can check whether he's seeing an actual spark on the antenna side, okay, on the receiver side, okay. And this experiment, his experiment was successful, okay. He was able to detect the sparks on the receiver side, okay, on the receiver side when we have a spark on the emitter side, okay. And so what he deduced is that there is a propagation of waves going from one part to the other, and this propagation is instantaneous, almost. It's instantaneous, okay. And it has to take the form of electromagnetic wave, right? Why? Because in order for these two spheres to have a charge, to have a spark, they must be charged. Right? So there must be the charge which was on the emitter side is transmitted to being a charge on the receiver side. Okay? And this is how experimentally Maxwell's equation and the fact that Maxwell's equation describe electromagnetic waves is demonstrated, is that the electric field variation on the receiver, on the emitter, propagated in space to the receiver and also generate electric field there. Okay? And he also measured the speed of this radiation of this, try to measure the speed of radiation. So let's go back to our mathematics. So experimentally, this was verified that with Hertz experiment, that Maxwell equations, they do, that the electric field and the magnetic field, they are transmitted in space in the form of what we're going to call an electromagnetic wave, okay? And it does connect two objects. And that's how actually you guys can now see me or hear me, because all this communication is done via electromagnetic waves, okay? So let's have some quite basic look about these electromagnetic waves. So as I said here, we're discussing the Maxwell equation, is that we have a second derivative in time equal to a constant multiplied by a time derivative in time, and a space derivative of b equal to a constant multiplied by a time derivative of b. We said that this constant you can verify actually at home, and this is a very good exercise. 1 over the square root of this constant of these constant is velocity, which is basically the speed of light. So we have now an oscillating electric field and an oscillating magnetic field. Okay, both have two properties. You can see that this kx gives me the oscillation in space, and the omega d gives me an oscillation in time. Okay, and so what we have is that the oscillation in space k is equal to 2 pi over lambda, where lambda is the wavelength, it's in meter, and k is what is radian per meter. And the angular frequency is omega equal to 2 pi f, where f is in second minus 1, or basically is in hertz. Okay? Now, the major issue that was discovered is that these electric field and magnetic field, the oscillation in space or the oscillation in time, they are linked together and they are not independent. And this link together is done via the speed of light. Okay? So omega over k is equal to c, which is the speed of light. And one can also demonstrate that E max over B max, that's the amplitude, okay, is also connected via the speed of light. Now, let me see if I have the connection. Now, the electric field, in terms of this is the amplitude of the electric field and the amplitude of the magnetic field. Now, in terms of directions. In terms of directions, we have 3 directions. If I have my laser, which is pointing in this direction, okay, so going horizontally, then in this case, the electric field will oscillate in one direction and the magnetic field in the other direction. Consequently, in such a way that the electric field, the magnetic field, and the axis of propagation are perpendicular to each other. So if E is in this direction, the propagation is in that direction, B will be in that direction. As it's shown in this curve here, where the magnetic field is the green oscillation and they occur in the YZ plane. The electric field is the red curve, and it oscillates in the XZ plane, okay? And then you have the propagation in the Z direction. From this propagation, we're gonna define the Poynting vector. The reason why I define the Poynting vector is simply to tell you, that's the energy, how the energy is the propagation of the energy, and this point is giving me E cross B. So it's basically it's perpendicular to the electric field and perpendicular to the magnetic field. Thus, the Poynting vector goes in the same direction as the propagation. Okay, so it's it gives you the magnitude of S represents the rate at which the energy flows through a unit surface area perpendicular to the direction of the wave that you have. But you know, you are more familiar with the intensity of the light. So we have, you know, light intensity, okay? The light intensity is basically the integration over time of the Poynting vector, and it has these expressions. I'm not gonna go into them. I'm not gonna go to. So let me, I'm gonna skip all this to go to the final part of this lecture, which is basically the electromagnetic wave. So what we said is that the Maxwell equations describe the relationship between the electric field and the magnetic field, okay? And this electromagnetic waves, they exist in nature in a variety of forms. Here you can see, for example, that's the electromagnetic wave spectrum, okay? So you can see that the electromagnetic waves, they go from the gamma rays to X-rays to UV, visible, of course. You can see me, I can see, I don't see you. Infrared, microwave, FM, AM, and low wavelength. All these waves, all these electromagnetic waves, they obey the same equations, and that are the Maxwell equations. And this is for this reason why this is the most important lecture, actually, because it tells you that what we are doing is of extreme importance. Because let's try to see if we try to do radio waves, okay, or microwaves. If you want to design a microwave, okay, what do you use? Maxwell equations. If you want to design radio waves, this means that if you want to emit radio waves, okay, the radios, you have to use Maxwell equations. If you want to design infrared waves or visible, okay, so this is the visible as you go from the blue to the red, passing by the green, also electromagnetic waves. Needless to say that each of these ranges, they have their own importance and their own applications. Let me start with the gamma rays. Gamma rays can be used for medical imaging. Okay, it can also be used to study the universe. So this is one type of usage. X-rays, I think that most of you are familiar with when you do an X-ray in a medical laboratory. So electromagnetic waves are, X-rays are electromagnetic waves. Their applications is also, could be to study the universe and to study, and for medical application, for medical usage. UV, ultraviolet waves, okay? This is your, for example, you get tanned by UV light from the sun. So this is at least one application. Visible, all kind of visible to the human eye is done in this range. So what you guys can see me, and so all these applications. Infrared application you can use, they are used for example, temperature. You know, now with coronavirus, you have these temperature measurement technique where they don't touch it. It's just they measure you via radiation, and actually what they measure is the infrared light, which is emitted by your body, and from this infrared light they determine the temperature and thus decide whether you can stay at home or you can move. But basically now we need all to stay at home. Microwaves, you all have microwaves at home, I guess. All the design and all the properties of these microwaves are done using Maxwell equations. TV, FM, radio waves, etc., etc., etc. These all are done using Maxwell equations. So the basic idea that I would like you to recall from this course, okay, as I mentioned earlier, that like I said that the bulk of this course is done, okay, and what we will be doing are more applications, is really to highlight the importance of these equations in solving like everyday problem. What you see on this graph here is one example. This is a nebula. A nebula is basically there was a star which explodes, okay, and by viewing this explosion in X-ray, which is the top left, in visible, which is the right, and the infrared, which is the bottom left, or in the UV, which is the bottom right. Each of these will give you an information about this nebula, okay? And consequently, studying the various components is very important to our understanding of our everyday life and also of our universe which surrounds us, okay? So this is basically what I wanted to say in this very important lecture. I'm gonna stop recording.